Hello class, today we're on 4.4 critical points in maxima and minima, where maxima and minima are just plural for maximum and minimum, and they are what they sound like they are. So let's first start with a critical point. A critical point is a point where the slope of a function is 0. So think about the slope and how that ties into the derivative. Well, the derivative gives us the slope, right? So what we're going to do is we're going to take the derivative and find out where the derivative equals 0. That will tell us where the critical points are. An absolute maximum or minimum is the absolute highest for max or absolute lowest for min point of a function. These will be critical points. So the absolute maximum min, the highest point or the absolute lowest point of a function. If there's a point where it goes higher than lower than that, it's not an absolute. A local maximum or minimum is the highest or lowest point in its area. These are going to be critical points as well. So a function can have many local maxes and mins, but there's not going to, it can have multiple maxes or mins. That's what I'm trying to say. Okay. So here I graphed the function for us, and here we have a local max, a local min, right? Notice that these this point is the highest point in its neighborhood, right? In its area, it goes down on both sides around it. This is a local min. It's the lowest point in its area. However, it's not the absolute lowest, right? Because the function goes lower than it. And then this is the absolute max of this function. Notice this is not only a local max, but an absolute max. It is the highest point of that function. And these are all critical points. Notice this is where this slope equals 0. The slope equals 0 right here. And the slope equals 0 right at that point. So these are our critical points. There is also one more critical point on here, and that's going to be right here. Notice it kind of squiggles. Well, there's a point where there's a singular point where it is completely flat, where the slope is 0. So this is going to be a critical point. However, not all critical points are maxes or mins, and this shows you how and why, right? Although this is a critical point, the slope is 0 at this point, and you would get that if you found the derivative and then set it equal to 0, solve for x. But sometimes critical points are neither maxes or mins, so we got to keep an eye out for that. So what we're going to do today is we are going to find critical points, and then we're going algebraically, and then we're going to use Desmos to help us determine whether they're maxes, mins, locals, or absolute, or neither, as in this case, right? So let's start with this example. Y equals 3x squared plus 6x minus 2. So first what we need to do is we need to take the derivative of it, right? The derivative tells us about slope. So let's see, what color am I going to use? Okay. So let's see, we're going to take the derivative, so dy dx equals, let's see, this is going to be 6x plus 6, that x goes away, and that negative 2 goes away. Okay, so we have 6x plus 6. Now we want to determine where is our critical point. So what we're going to do is we're going to take the derivative and set it equal to 0. So we're going to have 6x plus 6 equals 0, and solve for x. So we're going to subtract 6. 6x equals negative 6, and as you can see, x is going to equal negative 1. So this function only has one critical point. So we can say this critical point is at x equals negative 1. And let's determine what kind of critical point that is, whether it's a min, max, or neither. So I went ahead and I graphed the original function. This is not this isn't the derivative, it's the original function. You want to graph the original function. And notice that, let's see, at negative 1, which is what we got, there is a critical point right there. And this is going to be an absolute min because this is a parabola, right? It'll never go lower than that. So we can say, not minus 1, equals 1. I hope you guys caught that. X equals 1. And it's in absolute. It's an absolute min. Just like that. Okay, let's take a look at this one. Y equals x to the 4th minus 2x squared. So let's take the derivative. So dy dx is going to equal, let's see here, this is going to be 4x cubed minus 4x. Okay. So now what we want to do is set it equal to 0 and solve for x. Now, right away I see that each term has an x in it. So when that happens, let's try to factor out an x and see what happens. So let's see. We're going to set it equal to 0. 4x cubed minus 4x equals 0. And I'm going to go ahead and factor an x out, which will leave us with 4x squared minus 4 equals 0. Well, now that we have, oh boy, my brain just exploded. Oh, now that we have them factored, we can set each factor equal to 0 and solve for x. So this first factor, x, just going to be x equals 0, and nice, that's already solved for us. And the second one, 4x squared minus 4 equals 0. So let's solve for the unsolved one. This, we can add 4 to both sides, right? So we're going to get 4x squared equals 4. And then divide both sides by 4. You can see we're going to get x squared equals 1. Taking the square root, we get x equals positive and negative 1. Remember the positive and negative. That's going to be important here. So we have 3 critical points. We have one at x equals 0. We have one at x equals negative 1. And we have one at x equals positive 1. And let's go ahead and now use Desmos to determine whether these are absolute mins, absolute maxes, local min, local max, or neither. So I went ahead and graphed this one for us. And we get this function. So notice our 3 values, negative 1, 0, and 1. Negative 1, that's a critical point. 1, that's a critical point. Or 0, that's a critical point. And at 1, that's a critical point. So let's go through these and label these. So the one at 0, this is going to be a local max. Notice it's the highest part in its area, but it's not the absolute highest part of the function. So this is going to be a local max. And then we have negative 1 and positive 1. Notice those go down to the same value. So they're actually both the absolute min, right? It's the absolute lowest part of the function. And one doesn't go lower than the other, so it's a tie, really, of absolute min. So at negative 1 and positive 1, we have absolute min. Okay. This next one, let's see. So taking the derivative, we need to take the derivative first. So dy dx equals, this is going to be 24x cubed minus 24, what am I doing, 24x squared, and then the 1 goes away since it's a constant. Okay, so let's see here. Now we have the derivative. Now, again, I see x's in each term, so let's factor this thing. So I can actually pull out an x squared, or actually I can pull out a 24x squared, can't I? So 24x squared, and then that's just going to be x minus 1, just like that. And you can verify if you wanted to distribute this 24x squared back into it, you'd get this again, right? So now let's set each factor equal to 0. So we have 24x squared equals 0, and we have x minus 1 equals 0. Well, this one we would divide both sides by 24, which 0 divided by 24 is just 0. Take the square root of both sides to undo that square. X is just equal to technically positive or negative 0, but it's just 0 in this case, right? And then this one we would add 1 to both sides, and x equals 1. So here we only have 2 critical points. So we're going to have one at x equals 0, and one at x equals 1. So let's go ahead and determine now if these are absolute mins or absolute maxes, local min, local max, or neither. Here we go. So this is a good example. We said one at 0 and one at 1. So here's 0 and here's 1. Well, the one at 0, notice that it's one of these neither cases. It's not an absolute min, it's not a max, but it's still a point where the slope is 0, right? So at 0, we can just say it's neither min or max, or max or min. And then at 1, we can see that this is an absolute min. This is the lowest that this function goes. So it's an absolute min. All right. I have 2 more examples for us. Now we have x cubed plus 3x squared minus 2. So let's go ahead and take the derivative right off the bat. So dy dx is going to equal 3x squared, and this is going to be 6x, and then the 2 goes away, the negative 2 goes away, right? It's a constant. So now let's factor, and again, this looks like something that we can factor an x out. So we're going to have, let's see, I'm going to factor the x out, and then we're going to have, I guess I could factor 3 out as well, but I'm kind of feeling lazy. So we factor an x, so this is going to be 3x plus 6, and we're going to set that equal to 0. So 1, we have x equals 0. That's awesome. That's solved for us. And then we have 3x plus 6 equals 0. So subtract 6. 3x is negative 6. So x is going to equal negative 2. So this one we have 2 critical points. And we're going to have, let's see, we have one at x equals 0, or negative 2, and then one at x equals 0. So now let's use Desmos to determine what kind these are. This is a nice cubic function here. And again, these are the original functions. I'm not graphing the derivatives. I'm graphing the original functions. So we have a point here at negative 1 and one at 0. It looks like they're both local min or maxes. This is a max, this is a min, so this is a local max and a local min. So at negative 2, it's a local max. Yeah, that's a weird A. Okay. And at 0, it was a local, a local min. Awesome. All right, one last example for us. So let's go ahead and take the derivative of this one. So we're going to have dy dx equals negative 4x cubed plus 12x squared. And the negative 6 goes away. So let's go ahead and now set this equal to 0, and it looks like we're going to factor this one as well. This one, there's a lot of factoring in this one. So this time I'm going to factor out, just an x squared. I'm feeling lazy again. So we're going to have negative 4x plus 12 equals 0. And let's see, so that we have x squared equals 0, and then we have negative 4x plus 12 equals 0. So this, take the square root of both sides, you can see what's going to happen. X is just equal to 0 because the square root of 0 is 0. And then here we're going to subtract 12. Negative 4x equals negative 12. Divided by negative 4. X is equal to 3. So we have two critical points here. One at x equals 0 and one at x equals 3. And let's see what kind of critical points these are using Desmos. Okay, so here we have this function. So we said we had one at 0 and one at negative, or one at positive 3. Let's see, I wish it would focus here. Oh well. So notice the one at 0 is neither. It's neither a min or a max. And then we have the one at 3, that's an absolute max. So the critical point at 0 is neither min or max. And the one at 3 is the absolute max. All right, so this is finding critical points. Now think about why would this be important, and how would this be applicable? Well, think if you can model something using a function, you can find you can either maximize something or minimize something to either max profits or minimize cost, stuff like that. So this is used in that context quite often. Well, that's all I have for you all today. Have a good day. Bye.